The interaction between human-emitted aerosols and the Earth's atmosphere remains one of the most uncertain factors in climate science. Aerosols, which include substances like sulfate, black carbon, and organic compounds, influence the Earth's energy balance in two key ways: by directly modifying how sunlight is absorbed and scattered, and by indirectly altering the properties of clouds. Traditionally, these impacts have been classified into direct effects, which involve the immediate scattering and absorption of solar radiation by aerosols, and indirect effects, which refer to aerosol-induced changes in cloud reflectivity and longevity. There are also semi-direct effects, where aerosol heating affects atmospheric stability, indirectly influencing cloud formation. However, in practice, these distinctions are difficult to isolate in either observational data or model simulations, making interpretation complex. To address this challenge, the Intergovernmental Panel on Climate Change has recommended a more streamlined framework, focusing instead on the effective radiative forcing due to aerosol radiation and aerosol cloud interactions. This approach considers the net impact of aerosols on the Earth's energy budget, integrating both direct and indirect influences. In the 2014 study by Zelinka et al., quantifying components of aerosol cloud radiation interactions in climate models, the authors apply innovative diagnostic methods to quantify how aerosols influence climate through both radiative and cloud-mediated pathways. Unlike previous assessments that often inferred cloud-related effects by subtracting one estimate from another, this study directly computes these components using model simulations. Special attention is paid to distinguishing the contributions of scattering and absorption, and to understanding the influence of cloud presence on the radiative effects of aerosols. By focusing on global climate models from the Coupled Model Intercomparison Project Phase 5, the study seeks to identify where models agree, where they diverge, and what drives these differences, thereby enhancing our understanding of how aerosols shape climate. To understand how aerosols influence the Earth's climate system, the authors of this study conducted a comprehensive analysis using simulations from 9 global climate models that participated in the Coupled Model Intercomparison Project, Phase 5, or CMIP5. These models represent a wide range of assumptions and processes used to simulate climate behavior. The core of their approach involved specially designed model experiments where sea surface temperatures were held constant over a 30-year period. By fixing the ocean surface conditions, the researchers could isolate the effects of aerosols without the added complexity of ocean feedbacks. In these experiments, they compared a control scenario with pre-industrial aerosol levels to 2 perturbed scenarios, one with present-day emissions of all anthropogenic aerosols, and another with only sulfate aerosols included. The difference between these runs allowed the team to attribute changes specifically to aerosols, and even to separate the contributions of sulfate and non-sulfate aerosol types. To quantify how aerosols affect the energy budget, the study relied on a technique called the approximate partial radiative perturbation method. This approach uses model outputs to estimate how much of the change in reflected sunlight at the top of the atmosphere is due to different factors, such as aerosols in the atmosphere, changes in cloud properties, or changes in surface reflectivity. Importantly, the method allows the researchers to distinguish between the effects of aerosols acting directly on radiation and their effects mediated through changes in clouds. By systematically applying this method across multiple models and conditions, the study was able to robustly quantify the separate influences of aerosol radiation and aerosol cloud interactions, laying the groundwork for a clearer understanding of their role in climate change. The study found that the combined influence of aerosols on radiation and clouds leads to a substantial cooling effect on the Earth's climate system. When all anthropogenic aerosol types are considered together, the models estimate an average reduction in incoming solar energy at the top of the atmosphere of approximately 1.40 watts per square meter. This overall cooling is not distributed evenly between the two main pathways. About 25% is due to the direct interaction of aerosols with radiation, while the remaining 75% results from aerosol effects on clouds. The direct effect of aerosols primarily involves the scattering and absorption of solar radiation. Scattering by aerosols tends to reflect sunlight back to space, contributing to cooling, whereas absorption, particularly by black carbon, leads to warming. On average, aerosol scattering causes a reduction in solar energy of about 0.62 watts per square meter, while absorption offsets this by approximately 0.26 watts per square meter, resulting in a net cooling of 0.35 watts per square meter from the direct aerosol effect. Importantly, the presence of clouds significantly modifies this direct effect. When calculated under cloud-free conditions, the cooling from aerosols appears stronger. However, in cloudy conditions, part of the aerosol influence is masked. The study finds that clouds reduce the magnitude of direct aerosol cooling by about 50%. This masking occurs because clouds reflect sunlight themselves, reducing the relative contribution of aerosol scattering, and because the warming effect of absorbing aerosols becomes more pronounced over bright cloud surfaces. Turning to aerosol-cloud interactions, the study shows that aerosols increase the reflectivity of clouds by enhancing the number of cloud droplets, a process that results in greater scattering of sunlight. This mechanism dominates the cloud-related forcing, contributing to an average cooling of approximately 0.99 watts per square meter. Cloud absorption and changes in cloud amount play a comparatively minor role, with average effects of about 0.01 and 0.06 watts per square meter, respectively. The study also distinguishes between sulfate aerosols and other types such as black carbon and organic aerosols. When considering sulfate aerosols alone, the combined cooling effect is about 1.16 watts per square meter, slightly lower than the value found for all aerosol types. In contrast, non-sulfate aerosols tend to produce a small net warming effect, as their positive influence through absorption nearly balances or outweighs their cooling from scattering. Specifically, non-sulfate aerosols contribute around 0.29 watts per square meter of warming through absorption, and only about 0.15 watts per square meter of cooling from scattering. Finally, there is substantial variation across the climate models. The cooling due to aerosol cloud interactions varies more than that due to direct aerosol effects. This variation is mainly driven by differences in how models simulate aerosol impacts on cloud scattering. Even if all models were to agree on this mechanism, a notable portion of the spread would still remain due to differences in cloud properties themselves, such as cloud amount and optical thickness. These results underscore the dominant role of aerosol-cloud interactions in climate forcing and the importance of accurately representing these processes in climate models. In sum, this study provides a detailed and systematic breakdown of how human-emitted aerosols influence Earth's climate by interacting with both radiation and clouds. One of its central contributions is the clear separation of the aerosol effects into their distinct physical components, scattering and absorption by aerosols themselves, and changes in cloud properties caused by aerosols. This decomposition offers a much clearer understanding of which processes dominate, how they interact, and how they vary among different climate models. A key insight is that while both direct and cloud-mediated effects are important, it is the impact of aerosols on clouds, especially through their influence on cloud reflectivity, that contributes the most to the overall cooling effect observed in climate simulations. Importantly, the study shows that the role of clouds is twofold. They are not only altered by aerosols, leading to indirect cooling, but they also modulate how aerosols interact with radiation in the first place, masking some of the direct effects. This underscores the need to treat cloud processes as integral rather than secondary in the assessment of aerosol-related climate forcing. The analysis also highlights that differences between climate models in how they simulate aerosol-cloud interactions are the main source of uncertainty. These variations stem from differing assumptions about how cloud properties respond to aerosol changes, more so than from differences in the baseline state of clouds across models. This means that improving our understanding of aerosol-cloud interactions, especially the microphysical processes by which aerosols influence cloud formation, lifetime, and optical properties, could significantly reduce uncertainty in climate projections. Moreover, the study finds that even components traditionally considered minor, such as aerosol effects on high-altitude ice clouds, can have meaningful impacts on both short-wave and long-wave radiation, suggesting an area where further attention is warranted. Overall, this work demonstrates the value of targeted, model-based diagnostics in clarifying complex climate interactions. By applying consistent techniques across multiple models, it becomes possible to isolate key mechanisms, identify robust features, and expose the roots of disagreement. Looking forward, future studies should aim to integrate improved observational constraints and explore more detailed representations of aerosol composition and cloud processes. These efforts will be essential to refining our understanding of aerosol effects and, ultimately, to enhancing the reliability of climate predictions in a world undergoing rapid atmospheric change.